Money, money, money. You now know a lot of technical aspects of modeling and designing a PV system, but you know that's not enough to really determine if PV systems are viable in the real world. It's time to talk about the financial aspects of the PV system. So how do we compare the costs of different electricity generation technologies? And how do we estimate the effective cost of energy? The best way to do this is calculating the so-called levelized cost of electricity, or LCOE. In this video, you will learn what LCOE is, as well as the price trends of PV modules and PV systems as a whole. You will learn how to calculate the LCOE of PV, and we will compare the LCOE of various renewable and non-renewable technologies to assess the cost competitiveness of PV-generated electricity at the time of this recording. Finally, we will discuss the factors that affect the cost price of a PV system. Let's start by defining the levelized cost of electricity, or LCOE. The LCOE is defined as the cost per kilowatt hour of electricity generated by a certain energy system. It is generally used to compare the lifetime costs of projects based on various power sources. For the levelized cost, the overall costs of an energy plant during its useful lifetime are determined. Then, the overall energy production of the plant over its lifetime is determined. Using these two numbers, we can then figure out the LCOE of a given energy system. The calculation of the LCOE can get quite complex, depending on the number of parameters that are taken into consideration. In simple terms, if we know the annual yield of the PV system over its useful lifetime and the system cost, the LCOE can be determined using the shown formula. Here, IT is the investment expenditures over a year T. So if the lifetime of the system is 25 years, we take the invested value at the beginning and divide it by 25 if it was paid for all at once. The operational and maintenance costs over the year T are denoted by MT in this equation. FT denotes the fuel expenditure in the year T. And of course for PV, fuel costs are zero since we get the sun's rays for free. ET is the AC yield generated in the year T. R is the discount rate, which is a factor used to discount future costs and translate them into the present value. Finally, N is the financial lifetime of the system. The lifetime of a PV system is generally around 25 years. Let us now look at the LCOE for various utility-scale generation technologies. The levelized capital costs in orange are calculated by using tax deprecation schedules consistent with permanent tax law, which is specific to the region and the technology under study. The fixed operational and maintenance costs are shown in green. The advantage of renewable energy sources are the zero variable operational maintenance costs due to the absence of fuel costs. The variable operational and maintenance costs are shown in blue, which are present in fossil fuels and nuclear generation technologies. The transmission costs are shown in gray, which translate to costs incurred to access transmission lines. Hence, finally we can see that PV technology is getting increasingly competitive with fossil fuels with an estimated levelized cost of electricity of $85 per megawatt hour for plants entering service in 2022. Another aspect that controls demand is the cost price of PV technology. How does the cost price of electricity generated by a PV system compare to the electricity delivered by your energy company? To answer this, we have to look towards the learning curves. The learning curve is the graph which shows the cost price, or in this case sales price, is dropping in time. In time, the industry gets more experience. Progress in technology provides for better PV modules with higher efficiencies. This experience results in better and faster processing, leading to higher production yields. Upscaling of production leads to lower cost of the source materials. Learning curves usually show an exponentially decreasing cost price in time until the technology or product is fully developed. In this graph, we have the average global sales prices of a PV module in inflation-adjusted euro per watt peak. The sales price is plotted against the cumulative production in gigawatt peak. Important to note is the sales prices, discounting some fluctuations, follow a largely exponential decay. Currently, the average retail price of PV modules is below 30 cents per watt peak. Now, we will see how the cost price of a PV system is not only determined by the module. The red dots here show the decrease in the cost price of a complete PV system. As you can see, in the early days of PV technology, the system price was dominated by the module price. In the current situation, however, the contribution of non-modular components start to play the most dominant role. By non-modular components, we consider the balance of system components like the racking, wiring, inverter, and battery for standalone systems. Maintenance costs, such as the cleaning and repair, also need to be considered. The difference between the red and blue lines corresponds to the non-modular costs. The green curve represents the learning curve for non-modular components. This learning curve is not dropping as fast as the module price. This means that nowadays the reduction in the cost price of a PV system will be mainly limited by the cost price of the non-modular balance of system components. This shows the advantage of crystalline silicon PV technology with respect to thin film technologies. Crystalline silicon modules have efficiencies ranging from 14% up to 20%. Higher conversion efficiencies means higher yields per area. While the non-modular costs per area are the same, the cost price per watt peak of the non-modular cost will consequently be lower for modules with higher conversion efficiencies. In this video, I discussed the concept of levelized cost of electricity and how various factors can affect the effective cost price of PV systems. For the producer, the levelized cost is a valuable indicator of the cost competitiveness of a certain energy technology. It is also a good price point indicator since the producer will have to sell the power at a price greater than the levelized cost for the system to be profitable. In the following videos, we will discuss how the levelized cost of electricity can be used to study the cost competitiveness of PV and study grid and socket parity.